Kaiser.
I'm Ryan Cihanowyz.
And I'm Daryl.
For our final project, we chose to model a Honda CBR600RR transmission.
This is a picture of our final project. It includes gears, shifter forks, shafts, and parts on the shaft that weren't press fitted or connected. This view shows all gears meshing, even though that is not realistic.
There is also a series of bearings and snap rings in the actual assembly that are not relevant to the kinematics of our model.
Our project was basically based on the kinematics of the gears meshing and rotating, and seeing how one gear meshing would affect the rotational speed of another gear meshing.
This final assembly was constructed of 3 separate sub-assemblies. Since we had 3 group members, we decided to split it into the gears, transmission shafts, and the shifter forks. We will go into further depth about each of these assemblies in the next slide. Here's the sub-assembly of the gears. It consisted of 11 separate gears. Each of the gears that are touching consists of the same pitch. However, the radius and number of teeth vary on each of the gears. To create these gears, we started by creating a base model of the gear with the use of formulas. So the outer diameter, inner diameter, pitch diameter, and the pitch curve radius were calculated dependent on the number of teeth. This made it fairly simple, so that for each of the gears we could go in and insert the number of teeth and the pitch of the gear, extrude it, and the gear would already be created. This process was repeated, and each of the external teeth on top of the gear were then added. Here's the exploded view of the gear subassembly. Again, it consisted of 11 separate gears. Some of these gears pre-spun around the transmission shaft, and they had bearings in them, and some of them were driven by the shaft, meaning they had spline gear. Since this transmission is a dog box, the teeth on the outside of the gear would catch the next gear when the shifter forks move the gear left and right. When this happens, it will connect to the next gear and drive the output shaft at a different rotational speed. This process is repeated for shifting gears all the way through each of the gears.
These are our transmission shafts. The top shaft is the driving shaft, and the bottom shaft is the driven shaft. As you can see, the driven shaft has a press fit gear connected to it, and the top shaft has a ball bearing attached to the end of it. These shafts are made using part design and GSD. To get accurate measurements for the shaft, a caliper was used to measure each indent and overall length of each section of the shaft. Each shaft is a sub-assembly in itself, and the driving shaft consists of 3 parts, and the driven shaft consists of 2 parts. Below are the 2 sub-assemblies for the shafts exploded. As you can see, the driving shaft, the ball bearing, the inner race of the ball bearings and the balls of the ball bearings themselves were attached to the shaft, and then the outer race for the ball bearing was a separate part. This was decided because it was easier to create these 2 separately, and then instead of creating one huge design. Along with that, the driving shaft has a plastic ring that presses on to the end of the shaft. The driven shaft only has 2 parts, one being the shaft itself and another being a nut. clutch nut. Yup.
Here's an assembly view of the shifter forks. There are 3 different shifter forks. 2 of them are the same size, and for the being on the driven shaft, the other is on the driving shaft. For some reason, Honda marked them 1, 3, and 4, which made it very confusing searching for shifter fork number 2. But then, stamped on the other side, it says left, right, and center. So there are only 3. When modeling the shifter forks, one challenge was how to complete the stiffeners that are on the sides of the fork. In here, both part design and GSD was used. Part design was used to make the base shape, with GSD being used for the stiffeners and the other supports. Here's an exploded view of the shifter fork subassembly. This subassembly was actually, each of the forks was indexed incorrectly in the main assembly. Each of the holes in the base of the fork should all be on the same shaft, as they all will ride on individual slots on the shifter barrel when they are assembled in the transmission.
Throughout this project, there were a few problems that we ran into. One of the main problems was the creation of the gear and the mesh of the gears. At first we assumed the pitch of all 11 gears was going to be the same. However, this was not the case. As you can see in this slide, the gear that fits inside of the first gear, if we assume the pitch to be constant for all 3 of the gear became too large to shift into the other gear. This caused all of the other gears to also overlap and cause binding issues. This problem was solved by going back and iterating the pitch for the gears that mesh until the spacing between the teeth was approximately 0.05 millimeters.
This slide is the motion of our model. To create these kinematics, we had to add fixed parts to the model. The fixed parts were considered to be the shifter forks. The shafts were the 2 parts that we decided to be angle driven of the model. And then the gears were rigid to the shafts. The problem with this model was that the gear joints between the gears would not work. After hours of trying to get it to comply, we decided to run the shafts and have the shafts move at a certain speed dependent on the gear ratio. This allowed it to be played as accurate and make it seem like the gears are actually meshing.